Now, I want to direct your eye to something very specific here, and maybe you've seen it already. And of course, in the classroom, I could ask you. Right now, I cannot. It's a very teachable moment, so I love those in the classroom. But please go ahead and ask yourself if you see some relationship between the shear force diagram and the moment diagram. Look very carefully and tell me, well, you can't, but think about what the relationship here is. I give you a few seconds and then I will, of course, tell you what it is. Yes, you are absolutely correct. There is a relationship, and the relationship is the shear force is the derivative of the moment. So what is the derivative really? The derivative is the slope of the function, right? So here I actually have a slope that goes from 0 to 45.72 over a length of 4 meters. I say that again. I have a slope that goes from 0 to 45.72 over a length of 4 meters. And that slope, therefore, is positive 11.43. Take that in. The positive is important, and the 11.43. The positive means that we actually have a positive slope here, right? It goes from positive x to positive y. That's the indication of the slope here. It goes diagonal upwards in this case. And so that's a positive slope. And for every meter I go to the right, I'm increasing by 11.43, to no surprise. That's actually reflected in your moment equation. Now let's take a look at the next easier part, which is this one here. And you can see that the slope here is minus 23.57. Minus means it goes down, diagonally downwards, if you will, from left to right. And that happens over 2 meters. So 47.15 divided by 2 with a negative slope is actually negative 23.57. And then you can convince yourself that the distance between this point here, 45.72 to 47.15, is actually 1 meter, and therefore the slope is 1.43. So we're looking at a slope of plus 1.43, plus because it goes up here. So one important thing that we just discovered is that the shear force is really the derivative of the moment over x, right? So what we have done without noticing it is actually differential math, because if you take a look at this function, it's really the derivative of that. And that tells us one very, very, very important thing about the moment function, besides the ones that we already talked about. But please memorize this one here, right? That the shear force passes through 0 where the moment is maximum, right? If you have done derivatives in the past, and you did if you are in this class, then you know that the function that goes through 0, that is the derivative, reveals where the parent function actually has a maximum. And so this is true here, right? So we don't have a maximum here because we didn't jump from 11.43 below 0. We only jumped to 1.4. But here we jumped through 0, and therefore we have our maximum value here. And that's always true. And so this is actually a very important aspect to remember. And therefore I want you to highlight this and really engrave it in your brain so that we understand this formula here. And we understand that the shear force is really the derivative of the moment. And if you pay very close attention, you can see something else here, which is not obvious. It's not like in your face obvious as it is down here for this one. But here you can think of this as the load case, and let's call the load case actually W. So I'm going to call the load case W. And what you can see is that also relates to the shear force. Here's a constant, here's a constant, and here's a constant. And what is the derivative of a constant? Is 0, 0, 0. So really what we're looking at here is dv dx. And the reason I have not included an equal sign yet is one very important aspect. And that is something that is probably the reason why you did not see that this really is the derivative of this load case, or sorry, of the shear force diagram. It's because this is actually the negative. So the arrows here are pointing downwards, and therefore the W would have to be negative here. So this is negative, and now it's equal. So the inverse of the derivative of the shear force is really the load case. So if you want to put the minus on the other side, that's what that would mean. But this is very important for us to understand, and we clearly understand that there's a mathematical relationship between the load case and the shear force diagram, and there's a relationship between the shear force diagram and the moment diagram. You could, of course, do that the other way around, and you could state that the moment function is really the integration of the shear force function. The reason I haven't done that, some teachers would write that out as saying that, hey, the moment is the integrated shear force, but be careful, because what happens if you integrate, when you integrate a function, you usually end up with integration constants. And we do not yet know enough about that here in this class, how that relates. That will be part of the upcoming problems. But please understand that conceptually it can help you to think that this is the integration of the shear force. So the moment is the integration of the shear force, but you have to treat that with caution, because sometimes you have integration constants. One last word about the moment here, and another thing that we can use to really validate our results. Notice that everything here is a positive moment. And that makes perfect sense if you think 1 or 2 lectures back, when we actually defined how our internal forces are really properly arranged and properly defined. We said that a smiling beam that would like bend downwards has a positive moment on it. That's defined by the moment that turns clockwise on the left cut and counterclockwise on the right cut. Take a look at your note card. So we said that those moments always create a positive bending. And you can see this here in this diagram. So you can see that this beam must be smiling all the way from here to here, because from 0 all the way over to the 7 meters, 7 meters. So all the way over to the 7 meters, the beam is smiling. And of course, an engineer would never say that it's actually smiling. An engineer would say it's bending downwards, and therefore you have tension on the bottom and compression on the top. I say that again. So if the beam bends downwards or deflects downward, then you have tension in the reference fiber or on the bottom and compression on the top. And that is what we defined as positive moments, and therefore you can take this here as an indicator that we answered this correctly, because you can physically say that this is pushing down, this is pushing down, this cannot move, and therefore you must have a smiling beam, and the positive here indicates that it is a smiling beam. So as you can see, there are many valuable lessons that we can take away from only a simple problem like this one, as long as we spend dedicated time on really analyzing how they relate to each other, for example, and how engineers display them. So let me recap what we have seen here and what you need to be able to do in the future. You need to be able to draw the diagrams, and to do that you need to include the identifier, you need to always include the unit, you need to include the significant values every time something changes somewhere, and you need to indicate if it's the negative region or the positive region, because the negative and the positive region has specific meaning. So for example, positive bending means the beam is bending downwards. Negative normal force means that everything is compression, and so on and so forth. But we will talk about this more in future problems. For now, I believe we have a good introduction and a good overview of what we need to do, and now it's time to practice it through another problem. And then I think you're ready for your homework, but please don't be fooled. My experience in the classroom is that students tend to get confused if a single aspect of the problem changes. So for example, if there's another force that pushes up, or there's another distributed force somewhere, then all of a sudden the problem appears very different. And that is totally normal. At least that's how I felt when I first learned this material. I looked at it and everything looked different to me. But in reality, it's always the same. And you can always apply the rules that we applied here today. So please understand that that is the reason why we have so much homework in this class, because if we don't expose you to different scenarios, you think that it's all solvable with one method, and you'll be surprised in the real world how different things would be then. So practice makes perfect, and you have the chance here through your homework to really be exposed to many different examples that really help you to be very, very, very prepared. So what I guess I'm saying is you're welcome for all the homework. I know we sometimes disagree on the amount of work, at least students and teachers do so, but hopefully you will see at some point that it makes sense and that none of these problems is actually a waste of time. In fact, they prepare you for very specific scenarios until we are ready to really understand these problems in depth. With that said, I believe we have mostly everything in place to tackle the homework, but practice makes perfect. So let's go through one more example problem before we apply our knowledge in the upcoming homework. Let's move on to the next page.